Consider a polynomial map operating within complex three-dimensional space. This diagram displays a degree 7 polynomial map. Taking partial derivatives of its accretions constructs the Jacobian matrix. Calculating its determinant, variable terms cancel entirely, leaving the numerical constant -2. Because this is a non-zero constant, the map is locally invertible everywhere on its surface. However, the map behaves differently at specific coordinates. If we define 3 completely distinct input points and feed them through the function, they all result in the exact same output coordinate, -1/4, 0, 0. By forcing multiple separate inputs into a single output, this mathematical object breaks the expected link between local scaling and global geometry. That link was the basis of the Jacobian Conjecture, a problem in algebraic geometry first formulated in 1939. The mathematician Stephen Smale categorized it as one of the major open problems for the 21st century, placing it alongside the Riemann hypothesis in terms of historical difficulty. The conjecture proposed that for polynomials over complex numbers, local invertibility everywhere should strictly enforce global invertibility. This belief was rooted in the nature of polynomials themselves. Because they are rigid, well-behaved structures, mathematicians suspected they simply lacked the flexibility to fold back on themselves if they were locally smooth at every point. But the degree 7 counterexample we just demonstrated does exactly that. It preserves local smoothness while collapsing globally. After 85 years as an open question, this single map provides the evidence needed to settle the matter. The conjecture did not fall to a new theoretical framework. It was bypassed by the discovery of a single computationally verifiable anomaly. We can prove exactly how this invertibility fails by tracking the coordinates through the map. This plane plots the first input at 0, 0, -1/4, the second at 1, -3/2, 13/2, the third at -1, +3/2, 13/2. Following calculated vectors, all 3 converge onto the exact same location, -1/4, 0, 0. Because the coefficients and points are all rational numbers, this failure of invertibility is not unique to complex numbers. It holds true across the reals and other mathematical fields as well. This is a concrete, mechanical failure. Verifying it requires no high-level theory, only basic arithmetic. Finding a 3-variable, degree 7 polynomial like this requires navigating a search space that is practically infinite. Previous attempts to find a counterexample used massive computational filtering and binary trees to brute force polynomials with as many as 16 variables. Researchers often assumed that any potential counterexample would be much more complex, possibly requiring a degree of 100 or higher. While finding this specific map was difficult, the task of checking its accuracy is straightforward. This script executes the entire verification in 8 lines of code. It simply evaluates the polynomials at the given coordinates and calculates the Jacobian determinant. Any user with a laptop and standard software like Wolfram Alpha can confirm the result in seconds. In this case, mathematical truth is established not by institutional status, but by a Python compiler. The discovery was announced in an unconventional format, a casual post on social media. It was shared by Levent Alpöge, a Princeton PhD mathematician. But the equations themselves were generated by a specific AI model, Claude Fable. The announcement caused immediate debate within the mathematical community as researchers grappled with an AI resolving a problem that had remained open for decades. Skepticism remained high because the breakthrough arrived without a traditional paper or a human-written proof of the map's derivation. Machine learning researchers quickly requested the full chat logs of the session to see if the AI had reached the answer independently or through extensive human coaching. The resulting debate highlights a new challenge for the field. We can easily verify the final output of a machine, but we cannot yet audit the internal process that produced it. Since the search space is too large for raw brute force, the question is how the AI successfully identified this specific map. One leading theory suggests the model may have utilized a near-miss counterexample found in existing academic literature. Older papers described a map that almost worked but contained a structural flaw, a mathematical pole where the function became undefined. It is likely that the model recognized this flawed map as a viable starting point rather than beginning its search from zero. The AI extended the polynomial, making specific adjustments to smooth over the gap and eliminate the singularity. This targeted modification preserved the constant determinant of the original while fixing the global invertibility problem that had invalidated the previous attempt. This represents a shift in how machines are used in the field, moving from simple data processing toward the targeted repair of sophisticated theoretical models. An 85-year-old conjecture has been answered by a set of equations short enough to fit inside a single social media post. This case highlights a widening asymmetry in research. The generation of a breakthrough can be opaque, even while the verification remains absolute. We are left with a result that is mathematically undeniable, even though the internal steps the machine took to reach it remain shielded from view. When the proof is easy to check, but the origin of the logic is hidden, the definition of what it means to solve a problem begins to change. Synthiq Labs, from research paper to working prototype.